Thank you for having me. I know I've been to some of the conference sessions, and it's really interesting. There's a lot of kind of more researchy and academic and theoretical talks today. But today's talk is more about actual productionizing some of these systems into enterprise-grade, real, production enterprise-grade systems. So we'll be talking about how we built an AI orchestration framework for an enterprise architecture copilot that we built. Iman unfortunately couldn't make it today, so you get second best. You get me. So just a quick intro about myself. Just so you don't think I'm a marketing guy. They sent the marketing guy because Iman couldn't make it. Actually, I do have a PhD in AI. I always joke, but it was before it was cool. We were doing backpropagation on a whiteboard in those days, so that kind of dates me a little bit. But I'm currently co-founder and CTO of Cat.io, who makes, we're building this copilot for architecture, architects, enterprise architects, chief architects, CTOs, technical leads, and so on. I'm proud to say we won the best, coolest technology award at VentureBeat Transform conference earlier this year in San Francisco in June. So very proud of that. And I have a bit of a checkered past, as you can see. Pretty much I've been in technologies for most of my life. So the problem that we're solving at Cat.io is very, very personal to me. So what is the challenge? What are we trying to solve? The issue is that enterprises typically have complex architectures. They don't have dozens of components. They have hundreds, most likely thousands, based on our customer set, thousands of components that are multiple cloud accounts with various concerns like AI, security, layering. They each have different concerns, so on. And it makes it very, very complex to manage these things. There are no tools for people like us to manage this complexity of architecture. I mean, I've looked around pretty much all my career. Everybody, see, I told you I need to move. I cannot stay still. Everybody around me has tools. Developers have tools. Product managers have tools. Project managers have tools. Everybody. I just had whiteboards or PDF documents as an architect. That's all I had. So there were no data tools. So because it's a really, really complex domain. So the purpose is how do you build tools to tackle that kind of complexity? Because static tools are don't work for this kind of problem. Whether it's snapshots or whatever, they don't adapt. You've got single agent systems, whether it's Datadog or Dynatrace, whatever. They don't have the expertise, the cross-domain expertise. And running around yourself, which is what we used to do, coordinating all these things just doesn't work. It's broken. So what we needed is a reasoning system, not just automation, a reasoning system that gave us scale in terms of, sorry. Thank you. You just saved my life. Thank you so much. All right. Okay, let's go back to slide one. No. So what it gave us is what we needed, a reasoning system, but a reasoning system that gave us, scale, so we can produce tens and dozens of recommendations in parallel about your particular architecture, about your particular domain that is very, very, very specific at scale, but also does it at an enterprise scale. So it is reliable, because if you're putting production systems in large enterprises, they have to be reliable and they have to be explainable. Otherwise, nobody will trust your recommendation system at all. So that's kind of what we set out to build. I'm going to flash a couple of things here, and then we'll get back to them later. This is just one of the modules that the Cat.io tool provides. But in essence, what we're producing are a number of very, very specific recommendations, optimizations about your architecture that are very, very, very specific. And it comes from deep, deep understanding of your architecture. And they're very explainable. So this is an example of a recommendation where, it goes through a summary, impact analysis, gap analysis, all that kind of stuff. So it's very, very detailed and very, very specific to your architecture. Now, that doesn't come just easily. So, and the way we built it is this three-layered cake. And I'll just start at the top, and then we can start digging into each one of these layers. So at the foundational layer, we're on Bedrock, Amazon Bedrock. So what Bedrock gives us is access to large number of foundational models without us having to worry at all about infrastructure. We don't worry about infrastructure. It's just there. We just use the API and it runs. And it gives us, good reliability and a whole bunch of other things that I'll go into later. But that's the foundational model. In the middle, we use LangGraph. LangGraph is where our agents live. Is where we manage all the state of all our agents, because they have a large multi-agent system, and state and management of these agents lives in LangGraph, because LangGraph is really good at managing state. And I'll go into a lot more detail in LangGraph, how we use it coming up. And then on top of it, we use Flyte. Flyte orchestrates all the different agent execution contexts, because as I said, we have a lot of parallelization. We have a lot of agents that are running all in parallel. So we use Flyte to orchestrate that. And I'll show how in a little bit detail. But in essence, each layer focuses on its core strength, and they all integrate together. All right. Sorry, I apologize. I added some pictures on the slides. I was just playing around with Gemini while I was building the slides with the Gemini kind of, generate pictures button that they added to Google Slides. So I don't know, hey, not too bad, right? In terms of generated picture. Anyway, so Bedrock, let's start with that. So what Bedrock gives us is enterprise-grade inference and reliability. So we can run large-scale inference runs on Bedrock without, as I said, us having to worry about building infrastructure. It's all there, so it saves us a lot of time having to do a lot of the stuff by ourselves, because it just runs there. It gives us, for example, things like retry logic, which is very, very important for us, because we're running really large AI tasks, and a lot of times, whether you have operational failures, or you have, say the output schema for agent is too big and it fails on it, or the context gets too large. There's a lot of operational failures that happen that actually remedied really, really well, as you'll see, with like 100% success rate through retries. It gives us that. It gives us token management. So our agents are very, very token aware and elapsed time aware. So we're constantly tracking and managing tokens and time. So that comes really, really easily for us to do in Bedrock. And then, it gives us traceability and auditability. So we can track specifically what the agents are doing, how they're talking, how they're collaborating. So just some production configurations that were used that worked really, really well for us. We have like 1,000-second, timeouts for these complex analyses. So they'll time out and then they'll retry. We have, connection pools and a 3-tier retry strategy. This is from a lot of different trial and error. This has been working really, really well for us, that kind of configuration. So a system like Bedrock is giving us really, really essential enterprise grade, what I keep calling it, because in essence that's what we live when we have a product that is being used in large enterprise. It has to be what I call enterprise grade. So it has all these things built into it. So we don't have to do a lot of the stuff ourselves. We're still a small company, we're still a startup. So there's a lot of things that we could do, but it would take us way, way too long to do by ourselves. And we don't have the resources for it. LangGraph. So the meat of the sandwich, it's blinking on the term meat. Okay, the cauliflower, I don't know, sorry. Apologies for the vegetarians or vegans in here. Stop. Oh, okay. Well, the middle layer, the really important layer in the sandwich, in this 3-layer sandwich, is LangGraph. And LangGraph is what we use to run our agents. And I don't know why it's doing that. Let's take a second here. Can somebody from the disconnect and plug it in? Is your computer plugged in, sir? Yes, it is. Okay, that worked. Easier than rebooting. Okay, so LangGraph is where our agents live and work, and we have built this kind of execution plan into LangGraph. So an execution plan gives you really structured and repeatable way so that the agents are doing the same thing, while the way we've built it, it's very, very adaptable and dynamic. So every agent in our multi-agent system executes this plan, and it starts, I know it's kind of weird, it starts from here, but it starts from the plan from query. Every agent gets a query, it starts there, and then they generate a plan automatically, and then they start executing this graph. So the first thing they do is they check the plan, and they assess whether, what they need to do next. And from the check plan, they optimize an optimal path through this graph for the particular query that an agent is working on right now. So the agent looks and says, all right, of all the things that I have to do now, I should reflect, I should call another one, and so on. So they optimize the path. And then we have a reflect step. So the agent then will do a reflection, which is our quality gate. So the agent will sit and reflect on the existing plan and say, well, does this plan really address the results of the previous step? Do they address where we are? Does this plan really address what my task is, what I'm trying to do eventually? And then they have the option to replan or go to the actual loading step. And so as you can see, that gives you a lot of adaptability, because at the next step, if the plan is still valid and they need to act, this is where they get to do a bunch of potential different things. They could call another agent for a subtask, for example, a retrieval agent, an architectural retrieval agent, which we'll talk about in a second, because they need something that they are not allowed to do or they don't have access to the data to do. They can clone themselves, for example, if they decide that the task is too big and they need to break it down into parallel executions. They will clone themselves, or they will generate an error, in which case they'll go to retry. And then the final step in everything is a response. Finally, when everything all is done, there's a reduced step that coordinates everything, all the responses, all the agents are working on a particular task, and then generate the particular response. So this is it's an ongoing, every agent in our system is constantly executing this plan, generating new agents, spawning, cloning themselves, or spawning more agents, and so on, until the task is particularly done. So that's kind of how we use LangGraph, and LangGraph is really, really good for this kind of stuff, because there's a lot of state to manage, and there's a lot of coordination that does. I mentioned our multi-agent framework. So what are these magical agents that I'm talking about? So our multi-agent system really, in a sense, reproduces how decisions get made in a typical, enterprise architecture team. You have a chief architect agent who will direct and coordinate and task different architects with some tasks. And we have a number of staff architects who are very, very specialized in a particular domain, and they get tasks very specific to that domain. And there's a lot of collaboration and coordination between them, but at the end of the day, they each have a specific task. Now, the interesting thing to take a look on the right is we have established a permission-based delegation of concerns. That gives you, for example, built-in governance, so that no single agent can cross multiple different domains, and no single agent can, for example, generate recommendations that span multiple domains. So in the security area, for example, you can't have an agent from an infrastructure domain generate security recommendation or have access to security data without specific delegation from the chief architect. So this gives you separation of concerns, which is really, really powerful. It gives you audit trails, because now we can actually check that every agent is doing what they're supposed to do, and then check the conversations that they're having. And it gives you risk mitigation. So that's kind of how our agent systems work. Now, having run these things and experimented and run a lot of these things over time, over the past year or so, we have determined there's a couple different patterns, if you want, that we found very, very useful, that we talk about a lot, which is, there's two different main patterns: the single domain pattern and then the complex cross-domain pattern. So in single domain task, you have a staff architect that is specializing in a particular domain. They need information about the architecture, about your requirements, about what kind of company you are, and and so on. That'll go. It's a single task. They will go to a particular architectural retriever or requirements retriever to get the information that they need, and then that helps them solve a particular problem. In cross-domain complex tasks, as I said, partly because of the very, very specific domain specialization and the boundaries around permissions that we have, we need to have a cross-domain pattern. So the chief architect really is the one that coordinates various staff architects, and then each in turn can go to different architects. So that's kind of how the two patterns that we have work together. Now, because of the complexity of the task and the just huge amount of data that we have to deal with, like imagine like an enterprise architecture has thousands and thousands of components and relationships and metadata and so on, and we're running hundreds and hundreds of LLM calls all the time, we need to parallelize. There is no way to do anything in the real world without parallelization. So we actually we have parallel agent execution that are running consecutively and in parallel. So an agent, as I said, can call another agent and call multiple agents to perform a particular task, or they can clone themselves when they break down a task into multiple subtasks so they can work on various aspects of the task in parallel. Without parallelization, parallel agent execution, there is no way we could have done what we ended up doing in real time, at least. You know. Okay. I mentioned the architecture retriever and the requirements retriever a couple times, but the architecture retriever is a really, really interesting, at least to me and to techies like me, is a really interesting piece because imagine, you know, you have a very complex architecture deployed somewhere and you need really, really deep information about it because in order to give really good, meaningful, and useful recommendations, you need to really understand the deployed architecture and the architecture at a very, very deep level. And typically, architects are used like, you know, API calls, static calls, you know, drawings and whatever to understand that. But those things don't work well and they're broken. What we have taken is a graph-based approach. So we have a network X graph with 22 specialized analysis analysis tools to do this. So there's 3 types of analysis tools that are available to our agents. So imagine an agent that needs to understand at a very, very deep level your architecture and be able to answer questions about it. So the first set of tools is graph query tools. So we have automatic, through the graph that we've built, you know, hundreds of thousands of nodes, we can actually discover components. We can discover metadata about components. This, not just that you have a Kubernetes pod running. You actually know what it's running and why it's running it and all the configuration about every particular component. We can discover relationships, not just simple relationship. This component talks to this component, but we can discover hidden relationship, transitive relationships. We can even discover circular relationships. We can discover things like tech debt type of relationship, impact relationship. Even though they're not explicit, we can discover implicit relationships in the graph, in the architecture, and build that over the graph. We can do dependency and also. So those tools are available to the agents so that they can start building an idea of the graph. The other set of tools that are available for the agents are component criticality tools. We can actually understand at a deep level what every component does. We understand how critical it is in the architecture. We understand, for example, the blast radius of a failure of a component and so on. So there's a lot of criticality assessment tools that are available to the agent. And finally, we need to be able to detect something more subtle aspects of the architecture. So we need to be able to detect bottlenecks or isolation. So bottlenecks are where a component is really bottlenecking everything else, or isolation, where a component is just sitting on the side, really not doing a lot. So we understand that wise. And we use tools like PageRank or betweenness centrality. These are tools available, like this is what Google uses, for example, for their pages and so on. We use the same mechanism, same algorithms to actually get ideas about your architecture. So now we have this agent, this architecture retrieval agent that understands as a very, very, very deep level your architecture and can answer questions from the other staff architects about it. Can retrieve components, can talk about relationships, talk about purpose, talk about criticality, talk about all these things about your architecture. Okay, so now the top level, so we talked about Bedrock, talked about LangGraph. The top level of our system is Flyte. And Flyte, you can think of it as the backbone of the AI system. Flyte is where all these graphs, execution graphs that I showed you earlier, run in parallel. What Flyte gives us is the ability to run concurrent agents all at the same time with each of their own context, each their own set of tokens, each their memory resources. So we're running 1,000 to 1,500 megabytes per task. We dedicated CPU cores per agent execution, fault tolerance because of retries, so on. We get 100% success rate with the automatic. We don't have failures. So Flyte is where all these agents live. So if you think in terms of resolution, at the actual agent level, we run agents in LangGraph, but at the higher level, which is 56 tasks running in parallel, we orchestrate that through Flyte, because Flyte is really, really good at running these kind of separate contexts in parallel. So, as I said, you're running like 56 tasks in parallel with the resources, and every one of these tasks has its own environment. Okay, so what has this system given us? So some production performance metrics, because again, I know I keep insisting on being enterprise grade, because if it's anything less, we found that our customers will just not trust it that well. We've got 56 specialized recommendation tasks running, executed in parallel. We've got all these agents that I mentioned about, all running inside each of their controlled resources, and their own token budget, their own time budget, their own cost budget, and of course resources like memory and CPU cores and so on. We're orchestrating hundreds and hundreds, like 500 plus LLM calls throughout all this per recommendation, for every recommendation. And we're generating maybe 50 to 100 recommendations per run. So you can imagine all the LLM calls that we have to do. That's where optimization and parallelization come in really handy. And then at the retriever level, we're running 200,000 plus node graphs in parallel with our architecture, so that we give our architecture retrieval agents really, really deep understanding of the architecture. Now, in terms of reliability, we have 100% task completion requirements because of the power of having these retries. As I mentioned earlier, retries are really, really important for us because of the scale, the size of our context, the size of our output schemas, and just the complexity of the tasks that we're running. Sooner or later, something will fail. There's no question. So having these retries, these kind of large timeout retries, works really, really well. And then being able to track and trace path across all these three layers of the cake that I mentioned. So I'm mentioning cake and cauliflower and sandwich, so I'm hungry, I guess. Whatever you want to call these three layers is really, really important, being able to trace that. We have enterprise resource management, so we've got, as I mentioned, we're tracking and managing CPU time, we're managing memory, we're managing tokens, we're managing elapsed times. Our agents are all very, very, very aware of these kind of things, and then gives you real-time monitoring. And we actually have a visualization. We have built-in visualization of of these conversations, so we can actually go in and trace and say at any point of time, look at the graph of all the agents and their communications, and say, oh, this agent's doing this agent's doing that. Actually, just as a side note, I wasn't going to mention it, but since it says I have 10 minutes, so I have a little bit of time. Some of the conversations between agents are very, very funny. So I'm going off script here. But we've noticed in the early days when we first started building the agents, we would notice agents would say to another agent, okay, let me touch base with you on this next week. And we're like, okay, but you can't do that. No. So we had to put in a lot of these guidelines into our agents to say, we know you're getting this from the real world, but you don't live in the real world right now. You can't do that kind of stuff, right? So, and some really, really funny stuff. So it's very interesting to actually having the traceability and tracking the agent conversation to see what kind of stuff they're talking about. Anyway, so that's kind of these are the reliability metrics that we're getting. At the end of the day, in terms of quality improvements, we're getting structured output generation with schema, and I'll show you in a second what that means. Explainable reasoning, and then the tone is very consultative. So the recommendations that the agent produced are very consultative in tone, and of course multi-tenant isolation, because we cannot not have this in an enterprise system, right? So to get back to kind of what I showed you or flashed quickly earlier, just as an example of where we are. This is just a quick screenshot of some of the recommendations that we would be getting. And there's maybe about 60, 70 of these recommendations. So you can imagine each one of these recommendations running hundreds of LLM calls and traveling, you know, and traversing hundreds of thousands of graph nodes just to understand and be able to produce recommendations. So, you know, they are rated, there's, you know, with benefits and costs and so on. And if we're to look into a particular recommendation, as you can see, the tone is very consultative. It's not just do this. Explainability is a huge, huge, huge topic for us because our enterprise clients, architects would never, ever trust a system if they can't actually see the reasoning and understand why it's doing it. So we spend a lot of time on explainability, you know, and it's very, very well structured. We have an actual output schema that every agent has to follow when they produce recommendations. So you've got, you know, summary and impact analysis, gap analysis, business impact. We have things like benefit, cost, complexity, and so on that are rated for every recommendation. And these are all very useful, very practical, and actionable recommendations on optimizing your architecture. Okay? So just a quick kind of coverage of lessons learned. You know, architectural patterns. Separation of concerns is really, really important in multi-agent systems. And it works really, really well. We have every layer of that. I'm going to use the word cake again. Every layer of that cake is all those brownies they had out there. So for every layer of that cake, it specializes in very, very particular thing, and it does it really, really well. And being able to separate those concerns is really, really important. The other part of separation of concerns is that separating the concerns of every agent is really important so that you don't get, the agents don't get overwhelmed, and then you have traceability in domain and permissions and governance and auditability. So that's really, really important. The other part is, you know, we have built a configuration-driven design. So we use YAML, as you saw, for agent definitions, allows us to very, very quickly modify our agents and rerun them and try different things and experiment, as you saw in some of the code that I was showing earlier. And we use task-based execution, so there's no hard-coded scenarios. There's these task graphs that I showed you earlier that are very dynamic, very adaptable, and allow at every step for the agent to check and see if they're doing the right thing, and then be able to replan. Sorry, 2 minutes. Okay, and then the last thing is that observability must be built in, because without us checking in and monitoring and logging the agents, we would not have discovered a lot of the issues in the early days that led to today. On the performance optimization thing, strategic parallelization is important, as I mentioned, at the task level and at the agent level. So at task level parallelization with Flyte, and the agent level through LangGraph. Mentioned memory and token management. It's really important to make your agents very aware of tokens and their budgets and stick to the budget. Otherwise, you get kind of runaway processes that you know will eat up all your budget. And then, you know, fault tolerance, multi-level retry mechanism, degradation, and error handling are really, really crucial for us. I'm going to stop here. Thank you, everybody. We'll leave some time for Q&A. And if you have any questions or if you need to contact me, let me see. Yeah, my email is here. Okay. Question?
So in one of the slides about the controlled resource management, you showed there are fixed like limits of say 2 CPUs and a few hundred to 1,000 megabytes.
1 to 1.5 gigs of memory.
Yeah, why so small? Because agentic reasoning is super resource intensive, and then the token generation is memory intensive. Usually they need gigabytes and a lot of cores. And
agreed, but it's not as small as you think, because actually that's just for executing, for the agent execution. That's for the LLM. Now the agents are running inside that context, but they're making outside calls to LLMs. What maybe you're thinking about is that we are not, the agents themselves are not running inference at all. Okay. The agents are executing calls to LLMs that are running inference.
Tool calling, basically.
Correct.
That's why you don't need a lot of resources.
These are the 22 tools that I mentioned later on. There's a lot of tools that are just making LLM calls and tool calls and graph calls.
Got it. So you have tool calling, you also have some reasoning, you may have some generation. Like, why using fixed? Like, why don't you use like dynamic resource allocation, like Kubernetes DRA, so it's like more elastic, dynamic. Like so hard to estimate how much resource.
So yeah, yes and no. I mean, we ran a lot in the early days, and we've kind of converged to a understandable and what's the word I'm looking for? Predictable, replicable model that we can use. Makes it a little bit harder because one of the issues we had in the early days with dynamic resource is that you can put caps on it, but the caps are unpredictable. Predictability is the word I'm looking for. So that's why we ended up doing it that way. We've tried a lot of different things.